All right. Good morning, everybody. Welcome back. Uh, Quick announcements for this coming week. You have two online homeworks that are due this Thursday. Please do not leave for the last minute. And for this week, we were supposed to have in-class assignment, but I will move it to the next week. So therefore, for this week, we will have lectures on Monday, Wednesday, and Friday, okay? And then the last in-class assignment we will do next week, which is, I think, the last week of classes. Also, I think I made available on Canvas a problem worksheet for the final exam. So take a look at it. And then next week, before our last class, I will give more detailed instructions about how the final will run. Okay, so let's see where we left off. Okay, last Friday I showed you, go back here. I showed you how to draw the structure of covalent compounds using the Lewis notation. So always use those steps as your guide. And also you can use the Clark's rule to help you make decisions. Again, this is a guide. At some point, you have to judge if you are going to the right path or not, okay? So I can't do all the work for you. At some point, you have to use your knowledge to figure out the direction you are going. And the last example I showed was for the PCl3, okay? So for today, let's start with another example. So another compound formed between phosphorus and chlorine. So now let's take a look at the PCl5. So let's try to draw the Lewis structure for this compound. And let's see if this compound is possible to exist or if it is just a hypothetical compound. Okay, so let's count about a couple minutes and then try to do by yourself or at least start it, and then I will solve it with you after 2 minutes. Okay, so let's try to draw the structure of uh, phosphorus pentachloride. Let's see if this structure is possible and see if we have any problems with this compound. So we have here PCl5, no charge. So the first step is always to count the number of valence electrons.
Hi, I'm sorry. Are you supposed to be showing your drawing on the screen?
Oh, shoot. Yes, I
Sorry.
am. Let me, thank you very much. Oh, let me switch to my other screen here. Okay, I think now you can see it.
Yes, perfect.
Okay, thank you. Oh boy. Okay, so starting always counting the number of valence electrons because those are the electrons that are going to be used to connect the atoms. And if there are leftovers, we will fill up the octet of the elements in the formula. Okay, phosphorus belongs to the group 15, therefore 5 valence electrons. We just have one, plus chlorine. Chlorine belongs to the group 17, therefore 7 valence electrons. Attention here, because we have 5 chlorines, therefore we need to multiply by 5. 7 times 5 is 35, plus 5, that's a total of 40 electrons to be distributed, okay, among all the elements. So we don't have any charges, so we don't have to add or subtract any amount of electrons. The next step is to choose the central atom. The central atom is usually the largest element in the compound, and usually also the element that has that shows in the lowest amount. So for this case, we have phosphorus as the central element, and we are going to surround phosphorus by 5 atoms of chlorine. Okay? It doesn't matter where you place the atoms of chlorine at this point. So I'm going to arrange them in a random spatial position here. Okay, so we have to have at least one single bond. So let's represent here a single bond between phosphorus and chlorine. To show that the electrons are being shared, we are going to put a circle around the pair of electrons. Okay, to make the bonds, we spent 2, 4, 6, 8, 10 electrons. We had a total amount of electrons of 40. Therefore, there are 30 leftover electrons. The leftover electrons will be used to fill up the octet of all the atoms in the formula, starting always from the atoms on the outside of the structure. And if after that there is still leftover electrons, it will be dumped on the central atom. So each chlorine here has 2 electrons. To make it to 8 and fill up the octet, you need 6 more. So we are going to do that for all the chlorines because they are all equivalent. And let's count again the number of electrons in the structure, and let's see if there is 2 leftover electrons. For each chlorine, we needed to use 6 electrons to fill up the octet. So therefore 6, 12, 18, 24, and 30. Okay, so we spent all the leftover electrons. All the chlorines have the octet filled up, and they are therefore stable. Another way to represent this formula, and it's a much better way, is for each covalent bond, we represent it as a trace. Okay. And the electrons that are not being used for bonding, they are called lone pairs or non-bonding electrons. And I always want you to represent them. So that's how you would draw the structure of PCl5. And as we noted here, each chlorine has 8 electrons in the valence shell. Therefore, the octet is full, means stability. However, for phosphorus, we have a different situation here. The atom of phosphorus has 2, 4, 6, 8, 10 electrons in the valence shell. Okay, so each bond counts as 2 electrons, and those 2 electrons in each bond will belong to both atoms that are involved in the chemical bond. And we noted here that for phosphorus, we have 10 electrons in the valence shell, exceeding 8 electrons that we were supposed to have to achieve stability. So therefore, the question is, for PCl5, where each chlorine has 8 electrons in the valence shell, however, phosphorus has an excess of 10 electrons in the valence shell, the question is this compound even possible to exist? Is possible to exceed 8 electrons in the valence shell? Okay, so let me switch to my PowerPoint. Okay, so the question remains here. If PCl5 is possible to exist, seems like a violation of the octet rule, where phosphorus has more than 8 electrons in the valence shell after making all the bonds. And this is the first exception that we are going to study regarding the octet rule. So PCl5, yes, it is a compound that exists, and I even took a picture of the PCl5. It's a cream color, very crystalline solid. And here there is a special situation called octet expansion. Okay, so what happens here if we take a look at the electron configuration diagram showing here on the right side of the slide. We have the lowest energy orbitals are always 1s. After that, we start to fill the 2s orbitals, followed by the 2p. So here we are at the second period of the periodic table. When we move on to the third period of the periodic table and start to fill up the 3s orbital, next one to be filled is the 3p. And look here what happens. The 3d orbital has very, very low energy, and this energy is very similar to the 3p orbital. Therefore, atoms from the third period below, they can expand the octet and start filling up the 3d orbitals. Therefore, for any of the elements here in red, it is possible to accommodate more than 8 electrons in the valence shell. And when this happens, we call it hypervalence. Okay, so therefore, phosphorus, which is in the third period, can easily expand the octet and accommodate 10 electrons in the valence shell. Okay, so octet expansion will happen for any of the elements between the third period and the fourth, fifth, sixth, seventh period. Okay, so all these elements here can expand the octet and accommodate more than 8 electrons in the valence shell if needed. Okay, and now we are going to add one more item to the Clark's rule, and this item will help you to decide if you have expansion of the octet or not. For the first part here, we are going to follow the same order, and we are going to add here one more item for the Clark's rule. So now we can compare X, which is 6 times the number of non-hydrogen atoms plus 2, and subtract from the number of valence electrons. If the result of this subtraction is a number lower than 0, a negative number, then that indicates that you have octet expansion for the central atom. Okay, so the Clark's rule can still help you decide if you have expansion of the octet or not. Okay, so add up this fourth item to your notes for the Clark's rule, and then this is the complete Clark's rule. Okay, so let's do one more practice before we move on to the next topic. So noble gases, they are usually stable and they don't need to form bonds with other elements or within or among them to achieve stability. However, we can force some situations where a noble gas will be bonded to an element. And the very classic example is the xenon F4. Okay, so this is a quite stable compound. And our goal here is to draw the Lewis structure for this compound. Don't forget that your structure must show all the lone pairs in the molecule. Okay, so I will give you a couple minutes to get it started, and then I will start it and we will solve it together. Okay, use all the steps that I showed you. Use the Clark's rule to help you guide what kind of structure that you have, and then start assembling the molecule. Okay. So in the those problems to draw the Lewis structure of covalent compounds, the first step is always to count the number of valence electrons that you have for the compound, because those are the electrons that will be used to bond the atoms and fill up the octet for the elements in the structure. So therefore, let's do that. Number of valence electrons for xenon F4 is going to be equal to xenon belongs to the, oh, sorry, yes.
It's not showing your drawing.
Oh my God.
Sorry.
Thank you. Oh, oh, okay. Okay. There we go. All right. Sorry about that again. Okay, xenon F4. Let's count the number of valence electrons. Xenon belongs to the group 18. So therefore 18 minus 10, that's 8. So xenon contributes with 8 electrons. There is just one atom of xenon in the structure. So therefore, let's multiply it by 1. And now let's take a look at fluorine. Fluorine comes from the group 17. So therefore, each fluorine is going to contribute with 7 electrons. We have 4 atoms of fluorine, therefore times 4. No charges for the compound, therefore no need to add or remove electrons. We are going to have a total of 7 times 4, that's 28, plus 8, that's 36 electrons. Okay. So let's start arranging the atoms for this compound. The central atom here is going to be xenon. Okay. Usually the atom in the lowest amount in the formula, and usually the larger element as well. And just place 4 atoms of fluorine. We are not worried with the spatial distribution of the atoms at this point. So it's going to be a random placement here. Okay, so now let's use the Clark's rule to help us guiding to see if we have single bonds, if we are going to have some sort of octet expansion, or any sort of multiple bonds like double or triple bonds. So let's draw here a separation. So now let's use the Clark's rule. Okay, so the Clark's rule is going to compare X, which is 6 times the number of non-hydrogen atoms in the structure plus 2. So that's going to be equal to 6 times 5 plus 2, and that is 32. Now we are going to compare X with the total number of valence electrons. For this specific case, for xenon F4, we have that X minus the number of valence electrons equal to -4. This negative sign here indicates that we have octet expansion. Okay, the Clark's rule is not 100% precise, but it gives you a strong indication that you are going to have octet expansion. So now let's distribute the electrons among the atoms to see if that prediction is true or not. If this is a compound, it must have at least single bonds. We are going to indicate that these electrons are being shared by making a circle. And again, let's count how many electrons we used to make the bonds. Just to make the bonds, we spent 2, 4, 6, and 8 electrons. However, we have a total number of electrons of 36, which means that we have 28 leftover electrons. The leftover electrons will be used to fill up the octet, starting with the atoms on the outside of the structure. And if there are still leftover electrons, it will be dumped on the central atom. Okay, so each fluorine has 2 electrons. To complete the octet, we need 6 more. So we are going to put 6 starting with the fluorine at the bottom, 6 more at the fluorine on the right side. And I'm going to do that for all the fluorine atoms in the structure. Okay, so now let's count how many electrons we needed to use to fill up the octet for all the fluorine atoms. Okay, 6 for each one, 6, 12, 18, 24. Okay, so we used 24 electrons to fill up the octet of all the fluorine atoms. We had 28 to do that. So therefore, we still have 4 leftover electrons. Those electrons need to be accommodated by someone. The only option here is to be accommodated by xenon. So therefore, xenon will take the remaining 2 pairs of electrons. Therefore, there is expansion of the xenon octet. Another way to draw this structure is to represent each bond by a solid trace. And I always want you to represent the non-bonding electrons in the structure, because that's going to be really important in the future. Okay, so with that, that's an example when an atom expands its octet. And remember, the elements between the 3rd and 7th period are the only ones that are capable of expanding the octet. And the reason for that is that they have a d orbital with very similar energy compared to the p orbital. Therefore, they can be used to make the chemical bonds and accommodate non-bonding pairs of electrons. Okay, very good. At this point, we are ready to start the next topic here. So covalent compounds, they will always have chemical bonds where electrons are being shared. And those electrons being shared, they are always in between the 2 elements. And remember that they belong to both elements. However, anything that is shared usually one of the parts have, it's like attracts more the electrons close to itself compared to the other element. So in other words, if we have a bond between xenon and fluorine, ideally the electron pair should be halfway between xenon and fluorine. However, usually the pair is close to one of the atoms compared to the other one, because different atoms, they will attract with different strength the electron pair. So is the real situation represented by that xenon attracting more the electron pair compared to fluorine, or the other way around? Is the electron pair closer to the fluorine than xenon? How can we decide where is the location of the electron pair? And let me go back to the other screen. Okay, so to decide where the electron pair is located, or which element attracts with more intensity the electron pair, we are going to analyze a property called electronegativity. And electronegativity is intimately related to the radius. Remember that smaller elements, they will attract the electrons with higher intensity. And electronegativity is going to reflect that. Therefore, electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. Higher the electronegativity of the element, higher the intensity that this element will attract the pair of electrons in a covalent bond. As you can see here in this scheme, fluorine is the atom with the highest electronegativity because it's the smallest one. And we are going to follow fluorine. The next one is oxygen. Then we are going to move on to nitrogen. Chlorine has a very similar electronegativity. And here is the order that we are going to follow regarding electronegativity. Fluorine, oxygen, nitrogen, chlorine, bromine, iodine, sulfur, carbon, phosphorus, and hydrogen is one of the lowest electronegative atoms in this series. Atoms on the left side are more electronegative than atoms on the right side. Okay. Okay, so now that I showed you the concept of electronegativity, that's a good point to start defining polarity of chemical bonds. Okay, polarity of a chemical bond means that one of the atoms has a higher electron density than the other atom involved in the bond. Okay, so that means one of the elements will pull the electrons closer to itself and leave the other element with some sort of deficiency of electrons. To show you how we defined polarity of chemical bonds, how we find if a bond is polar or not, let's use the example here of the CO2 molecule, the carbon dioxide, and I'm also going to show you the example of the Cl2 molecule. So let me switch to my other screen here. Okay, so let's take a look at the CO2. So it doesn't matter at this point, but CO2 has a double bond between carbon and one of the oxygens, and another double bond between the carbon and the other oxygen. So the polarity will tell you if those electrons shared between carbon and oxygen are closer to one of the atoms or if they are equally shared. So because the compound is equivalent, we have double bonds in both sides, we are just going to analyze one of the sides to be more convenient. Okay, so if those elements had the same electronegativity, the pair of electrons being shared would be exactly halfway between the two atoms, is a perfect share, perfect world. However, if we take a look at the polarity scale, we can see here that oxygen is much more electronegative than carbon. The result of the stronger electronegativity of the oxygen compared to the carbon is that oxygen will pull the electrons in the chemical bond close to itself. So in reality, if we could take a picture of this chemical bond, we would see the pair of electrons much, much closer to the oxygen compared to the carbon, okay? So oxygen pulls this pair of electrons very close to itself. That creates polarity, okay? So oxygen, because it pulls the electrons close to itself, has high electron density. On the other hand, if one side has high electron density, the other side of the chemical bond has low electron density. And we are going to represent that we are creating a pole in the chemical bond using a vector, okay? The vector will always start on the low electron density side and point to the high electron density side. And I'm going to draw a trace here. So this vector indicates that the electrons are flowing from the carbon towards the oxygen. And that is a result of the different electronegativity of oxygen compared to the carbon. To represent that we are creating a negative and a positive pole, we are going to use the symbol delta. Okay, so this symbol belongs to lowercase delta. So don't confuse to uppercase delta. Okay, so therefore we have a delta minus on the oxygen because we have high electron density over there. And therefore we have a delta plus at the carbon because we have low electron density at the carbon atom. So you may see this kind of representation like usually like that. Okay, so a delta plus and a delta minus. It doesn't matter the magnitude of the delta, is just a qualitative representation here for us. Delta plus indicates low electron density and delta minus high electron density. And this will always happen in covalent compounds because we have electrons being shared. We can also represent that drawing a vector that starts at delta plus and points to delta minus. When we create the polarity, we can label this bond as a polar covalent bond. The meaning of a polar covalent bond is that the pair of electrons is closer to the most electronegative atom involved in the bond. Okay, so if we analyze Cl2, we have a single bond between chlorine and chlorine. Now let's analyze the electronegativity of the two atoms involved in the bond to figure out if there is a stronger pull from one of the atoms relative to the other one. Chlorine and chlorine, they will pull the pair of electrons with the same magnitude. Therefore, we cannot create an accumulation in one side compared to the other one because they pull with the same intensity that cancels the vectors. Therefore, we don't have any poles in this chemical bond, which means the bond between chlorine and chlorine is a non-polar covalent bond. The meaning of that is that the pair of electrons is being perfectly shared, is exactly midway between the two atoms of chlorine. Okay, so with that, I will finish here and I will see you tomorrow for the discussion. Have a good week.
Have a good rest of your day.
Thank you.